All right. Okay, we're gonna start with chapter 3. Chapter 3 is yeah, it's not. So what we're gonna do is we're gonna study by we're gonna talk about critical number and extreme value theorem. So let's review all the theorem that we have encountered already. The first major theorem you guys remember is what? Theorems. Can you tell me any theorems? There you go, into theorems. Intermediate value theorem. Basically, intermediate value theorem is like a water bottle. You have the function must be continuous, so continuous between a and b, right? And the f of a does not equal to f of b. That's the two condition. And also c is between a and b. So f of a is less than f of c and less than f of b, and basically there must be a value, there must be a c that f of c is equal to k. I'm sorry, this one is k. Okay, there must be a value. There must be at least one value, at least one c. So make sure at least one c. F of c is equal to k. Okay, so that's the intermediate value theorem. The second one is squeeze theorem, and you guys probably don't remember anymore, but that's okay. You can look it back up. This the squeeze theorem. Now the chance of that happening of squeeze theorem are roughly 2%. So it's not a whole lot of percentage that can happen. Maybe I can increase to 5%, maybe. But intermediate value theorem, definitely, you're gonna have 40% of the theorem problem. It's gonna be about intermediate value theorem. But another major theorem is later we're gonna do is rules theorem. And the fourth one is gonna be mean value theorem, which is we're gonna cover end of the week. Okay, now this one is like a 50% of the problem. 50%. It's on every single exam, but it's on half the problem. Let's talk about things. So we kind of talk about this today, like where instantaneous rate of change is equal to average rate of change. That is called a mean value theorem, but we actually kind of talk about it today. But what we're going to talk about, the major thing we're going to talk about today is this one, is the extreme value theorem. Okay, extreme value theorem, that's happened all the time. Now, what is the extreme value theorem? Extreme value theorem is very, very easy. You just say f must be continuous. F must be continuous. And make sure it's a comma b bracket. So make sure this is a close. Why is close? And that's very, very important. And that's I would say that's very important. Why is it closed, not open, right? So that's a very, very super important there. And then what it says result is going to be f has minimum or maximum within A and B. It must have a minimum, a maximum. And you're going to be like, how can a graph has no minimum, no maximum, right? How is that possible? I'm going to show you two cases that's possible. One is they are not continuous. So there was a lot of showcase like if it's not continuous, right? Then can I have a maybe between A and B is there is a vertical asymptote, something like this, right? So there is no maximum, there is no minimum because you cannot say maximum is infinite or negative infinite because that's not a defined value. So it's not going to work. So A and B must be continuous. That means there's no vertical asymptote. Okay, so what other thing can be no vertical asymptote? Well, I can have a function. So this is no max or min in this case, right? What if I have something like this, right? Now, what if I have some A's right here and B's right here? And then I say, hey, I have an open circle here. So technically, I don't have a minimum. You can say, well, minimum point is about right around 2, but the problem is I cannot define what? 2. Is it 2.01 or 2.001 or 2.0000001 or 2.000000001? I don't know how the minimum is. It's not definable. Even though roughly this is around 2, but we don't know what is the exact value. So there is no minimum in this case, right? No min. There was a max. There's a max. This is called endpoint max. So there was a max, but there was no min. Does that make sense? So we don't know what 2 of that. We know there's an open circle at 2, but we don't know what happened. So there's also another way to think about this is this. Why does endpoint matter, right? What if I have something like this? I have this solid dot right here. Right? I have a solid dot here, and I have a continuous functions into here. So obviously I have a minimum here. But do we have a maximum? No. We really don't know how to define is that 6.9 or 6.99 or 6.999 or 6.9999. I really have no maximum here. So there is no max.
Did you say 6.9 represented?
Huh? It didn't matter. Yeah. It didn't matter. Well, how do I know it's not 6.8? I mean, my graph looked like this, right? It's an open circle like this, but do I know is it maybe that point is like 6.8? Maybe at 6.6? You never know because we don't know how wide that circle is. I didn't define it. Did I say that center has to be there? No, it does not define. So you don't know how close is it or how far is it. We know it's something greater than 6.
I thought that anytime that there's an open circle, that it's just that one point at 7.
Well, can I have an open circle at 6.99? Yep.
No, I just thought that it had to be.
No, it doesn't have to be. It appeared to be, yeah, but it doesn't have to be. If I show you like a 6.99, then you still have open circle there, but in your visual eye, you're not able to tell whether that open circle is like 6.99 or 7. Because it's really hard to define that, right? So it's really not possible to find a maximum minimum. So that's EVT, which is extreme value theorem. There was extreme value theorem, it's continuous. It does not happen to be differentiable. However, there are a lot of theorems that need to be differentiable, which is rules and means those are has to be differentiable in order to work. But this is not the case. Okay. Now we're going to talk about what is critical number. So critical number okay, what is critical number? The critical number occur at f prime of x is equal to 0. Sorry, f prime c. C is a number, not x. X is a variable, so it has to be f prime of c. C is critical number. So today you had to find critical number. Also, the second one, usually people forget. I mean, use a different color to represent this. It could be equal to undefined as well. And here, C is also a critical number. But usually people forget about this one. So it's two things right here. The first one and the second one. So that is a critical number. So you're going to be like, how is it undefined? Well, what if you have f prime of x equal to 2x over x minus 1? Maybe to the 2-third power like this. Okay. Guess what? You have two critical number here. This is f prime x. You can set the numerator equal to 0. It's this for the top. Because of top equal to 0, that's critical number. Or the bottom. It doesn't matter 2-third power. So you can have two critical numbers. Two critical number in this case. If I have f prime of x equal to 2x over x minus 1 to the 2/3. So you have to pay attention to those. Now, what's the nice thing is this. There are two illustrations of this. One, the function does not have to be continuous or differentiable. So I can have a and b here. I can have something like this. That is not differentiable. But it's still a critical number. A C is still a critical number. Now I can have this between A and B. And I have something like this. And this C here is f prime of x is equal to 0. So I can have that. That's called a relative maximum. So critical number is when f prime of x is equal to 0. F prime of c is equal to 0. Take a derivative, set it equal to 0, 0. Set it equal to 0. Or take a derivative, set the denominator equal to 0 as well to find out what the critical number is. Now, if I would tell you the other way, if I says f of x, f of x has a relative maximum, then or minimum, so or minimum, then at maybe at x equal to c, then c must be a critical number. It has to be. There is no other way around. It must be, because if I have a peak, that means there's two type of peak. One is a cusp. Guess what? You have relative maximum. The other one has a normal peak, then you have relative maximum. So at that peak, it could be a critical number. It has to be. So it has to be critical numbers. How much time I have? What?